Welcome to the Math Record. Today we'll be covering the chi-square test of independence. This video would cover chapter 4 of part 3 of our statistics class. Okay, a chi-square test of independence. Squared test of or for independence, doesn't matter. Just tell them it's a dependence. So basically, this, as I said before, a chi-square test of independence is, in our previous video, it's basically you compare elements from one sample. So a chi-square goodness fit uses a frequency table. A chi-square test of homogeneity uses two samples, and it compares the two samples. And then you have a chi-square test of independence, which is one sample, but it uses a contingency table like a chi-square test of homogeneity. But now you have to compare the independence, like if one element of that is independent of another. So first up, you always want to check the conditions. So this is similar to basically the goodness of fit and the chi-square test of homogeneity. So you have count data. So the data could be counted. So if you have if you are like given red, blue, and green marbles, you should be able to count the amount of red, the amount of blue, and the amount of green marbles. Then it has also be independence, right? So the data is independent, basically. So just because I just write it as IND, independent. So just because you get a red the first time doesn't mean it's gonna affect the probability of you getting red the second time. So you flip a coin, heads the first time doesn't mean you're guaranteed to have tails the next time just because they have 50-50 probability. So it's not guaranteed. So independence. And now you have random. So the sample has to be random, so you reduce bias, right? The sample is random. Usually they give you this in the question, so you just have to write it down. 10% condition, which is your sample size, which is n, has to be less than 10% of the population, right, of whatever you're observing. And as always, you have the expected cell frequency. For chi-square tests, there's always the expected cell frequency. The conditions are basically the same for every single chi-square test, except sometimes you don't have to use the 10% condition. It's optional, but you don't have to do it all the time. So it says that each cell for your expected has to be greater than or equal to like 5. So let's say you have a like a chart, right? Like this is the example I used in my previous video. So sorry. You have 10 here. Your number here was like 35. This was like 20. This is like 55, and let's say 60, right? So that is a total of 80, 90, 110, and 170, right? You have 170. So let's say your expected was I don't know, 40, then 30, then let's say a 40 again. So that's 80, that's 110, and then this one's 60, right? So basically that your expected is 40, 40, 30, and 60. This is your actual sample. This is your expected. So your expected cell size is 5. So the 40, 30, the 40, and the 60 are all greater than 5 for each cell. So you could say the expected cell frequency is met. And then basically after this, you do a transition statement as always. So you tell them which test you're doing. Statement. So you say it's basically the same thing as every single other test since the conditions are met. Sorry about that. Conditions are met. I can construct a chi-square test of independence. Square test of independence, or for it's for or of. It doesn't matter. You just need to tell them its independence. So just write that down, and then basically you're done with your transition statement. Okay, your actual test, which your null hypothesis (HO) is that the basically the whatever you have to put inside the context. Basically, the individuals are independent of each other because you're talking about the elements inside the one sample. So basically, you just have you have to be very specific about this. This is why it's really vague now, and I said individual. It will explain more in the example when I show on. And then the alternative is that the individuals aren't independent, basically. So that's the test. As always, you don't have to define your variables for a chi-square test because, like, usually you're just gonna test your distribution, and the chart array tells you all the information they basically need. So, the mechanics, which is the math portion. So, your x squared value is basically the same thing. Is it's the summation of so the sum of the observed, which is OBS, which I will write as OBS, minus the expected, which is EXP. Square that number, and then divide it by the expected, and you have a degree of freedom, like a t squared, like a t model. There's always a degree of freedom. This is the same idea as the chi-square test of homogeneity. So it's degree of freedom of the rows minus 1 times the columns minus 1, right? And then you usually use an alpha level of 0.05, unless they ask you to like 10%. As I explained in other videos, usually if they don't specify, it's just 0.05. And then you have your p-value is equal to your x squared with that degree of freedom, basically, is greater than or equal to whatever your x squared value is. So this value is is this value that you calculate. It's basically the same idea as the goodness of fit, in the chi-square test of homogeneity. The mechanics in general are basically the same idea. It's just observe minus the expected and then square that number and then divide by expected, and then you sum everything for that. It's just that sometimes degree of freedom is different. So, and then you basically draw a picture and to like see if it to get the general idea of how it looks. So something like this, right? So let's say it's right here. Your x squared value is right here. So you just color in everything. Okay. Now let's do the conclusion, which is pretty similar all the time. It's the general idea is always correct. If your p-value is greater, I mean less than 0.05, your alpha level, you say the null hypothesis is false, and your alternative hypothesis is true. And if your p-value is sorry about that, p-value is greater than 0.05, then you say your null hypothesis is true, and your alternative hypothesis is false. So it's just vice versa, depending on which your p-value is, and if it's higher than your alpha level, which is usually 0.05. And then you have to write this in context, so don't write this, as I said in previous video. So if your p-value is less than 0.05, your alpha level, say based on the p-value of whatever p-value is, which is less than the alpha level of 0.05, I reject the null hypothesis. Talk about your null hypothesis. There's evidence to suggest the alternative hypothesis is true. So talk about your alternative hypothesis. Always put everything in context. So as the more specific you could to put in a question, the better your answer is, because it's particular for that question. And then if your p-value is greater than 0.05, your alpha level, say based on the p-value of whatever your p-value is, which is greater than that the alpha level of 0.05, I fail to reject the null hypothesis. There lack evidence to suggest the alternative hypothesis is true. Talk about your null hypothesis, your alternative hypothesis. Put everything in context all the time. Okay. So as always, a chi-square test does not have a confidence interval. Only a z model and a t model have a confidence interval because their models are symmetric. So as a normal model and like something that's kind of like more squished down for a t model, those are symmetric. While a chi-square test a chi-squared is skewed, so we can't use a confidence interval. Okay, so now let's work on an example. So let's draw a chart out. Okay, and we have 1, 2, 3, 4, 5, 6, and we have 4, 2, 3, 4. Okay, and let's males, females, red, blue, green, and yellow. And you have 91, 55, a 26, a 15, a 53, a 17, a 26, and another 17. So that's 196, that's 104, and that's 300. This is 146, 41, 70, and 43, right? So the amount of reds is 146, so you just add that to get that number, this to get this to get this, and this to get this. And all these numbers add up to that, and all that number to add up to this. And all these numbers add up to this, or all this number add up to this. It's basically the same idea. So this is a contingency table. So the example is a chocolate company tests one group, so it's one sample. So of 300 people, so our sample size is 300, and asks for their gender and their favorite chocolate color. The table below records the results. So the question is gender independent of choosing a favorite color, chocolate color? So basically, we have males and females, and we have to compare that to the gender to color. So males and females gender, and color is the red, blue, green, and yellow. So it's compare are they the same? So because we have a 996 for males, the amount of male we have a 196 males and 104 females in our sample of 300, and we have to compare if like the 91, 26, 53, 26, 55, 15, 17, 17 are like that unusual for them to be different from each other. So it's gender independent of choosing fair color. So it'd be like if just because like a male chose like red, just because he was male, he had a higher chance of choosing red. So there might be a different reason. Like males tend to have like a more favorite color, than females. Like for example, like maybe males like red more than female, and we need to see the distribution for that. Okay. So first up, always check your conditions. Always do your conditions. So your conditions is count data. It's always the same for every single chi-square test. Count. You could count the amount of you could count the amount of boys and girls, so you could count the gender, and you count the amount of you count the color of the chocolate. So you count the amount of red chocolate, the amount of blue, the amount of green, the amount of the yellow. Independence. So basically, um, males are independent. I mean, gender is independent of color. Is independent. I just put IND of color. So just because like a male chose red doesn't mean like a female would have like would be affected by that choice. So she won't have like a lower chance, a greater chance, or equal chance. It's just basically random. And then you have random. So your sample is random, which was given by a question, which just the sample is random, basically. Random sample of 300 people, right? And then sorry, kind of running out of space. So you have a 10% condition. So your sample size of 300 is less than 10% of the less than 10% of your population. Since you're measuring the male and female in the world, it's basically just everyone in the world. So basically, you're just saying the 300 is less than 10% of the amount of people in the world, because that's who you're measuring the genders in the world. So basically, the 10% would obviously be higher than 300 because there's like millions of people in the world. So, and then the knowing part, the expected cell frequency. So let's go back to our chart. We have to find the expected. So for like how we did for our previous example, you just look at our to get like a male red, right? We just have to multiply this number by this number and then divide by this number, right? So just multiply the number that's right down from it and right to the right of it, and then multiply and then divide by the total amount. And you do that for every single number, so for all 8 basically. So you want to get this one, use this one right here, and then this one divide by this one, right? So using your calculator, you could just let me make a chart. This is basically the same idea as the chi-square test of homogeneity. This is why I said in our previous video that the chi-square test of homogeneity and the chi-square test of independence is basically the same. They do the same math, it's just that they answer different questions. So you have a 146 times 196 divided by 300. And you get about 95.4. Okay. You have a 146 times a 104 divided by 300. And you get a 50.6. You get a 41 times 196 divided by 300. You get a 26.8. A 41 times 104 divided by 300, which is equal to 14.2. A 70 times 196 divided by 300, which is 45.7. And a 70 times 104 divided by 300, we get a 24.3. And we have 43 times 196 divided by 300, 28.1. And we have a 43 times 104 divided by 300, which is 14.9. So based on these numbers, like the 95.4 and the 91 is pretty close. 50.6 to 55 is pretty close. 26.8 and 26 is really close. 14.2 and 15 is really close. 45.7 and 43, it's kind of close. 24 and 0.3 to 17 is kind of close. 14.9 to 17 is kind of close. And 28.1 and 26 is kind of close. So based on like a general idea, these are like pretty similar distributions. So red, blue, green, and yellow. As always, like how I said for like the chi-square test for homogeneity, like the all these numbers will add up to basically the exact same number. So this would be all this will add up to 196. The second row will add up all to 104. The red column will add up to 146. And then the second is 41, the 70, and 43, right? So it's the same, basically. It's just that the expected change, so these values change. So our expected cell frequency condition states that each cell is greater than 5, and they're obviously all greater than 5. We have a 95, a 26, 45, 28, 50, 14, a 24, and a 14. So they're obviously all greater than 5. So we say that our conditions are met. So then you write your transition statement. I'm not going to write this down because I already did in the beginning of the video. Basically, just write what I have. So basically, your transition is, since the conditions are met, I can construct a chi-square test of independence. So our hypothesis test, right? Our null hypothesis, we have to put everything in context. So gender is independent of a favorite chocolate color, right? And then alternative hypothesis, HA, is gender isn't independent of fave. I'll just write as fave. chocolate color. Chocolate color. Okay. So that's your null and your null hypothesis and your alternative hypothesis. So it's independent and it's not independent. And now we do the mechanics, which is the math. So our x squared is equal to basically the same thing. It's like how we did for the homogeneity. Is the observed minus the expected. Square that, divided by the expected again. And then that has a degree of freedom, like a T model, of the rows minus 1 times the columns minus 1. And then you have an alpha level of 0.05, unless they actually change to like 10% or something. And then you put your p-value and you draw a picture. So let's go back to our actual table, and we had to like calculate everything. So we have the observed minus the expected, square that and then divide by the expected. So we have the 91 minus the 95.4, square that, divided by 95.4, plus the 26 minus 26.8 squared, divided by 26.8. And you do this for all 8, so it's just kind of tedious. So you have 53 minus 45.7 squared, divided by 43.7. 45.7, sorry. Plus a 26 minus a 28.1 squared, divided by a 28.1, plus a 55 minus a 50.6 squared, divided by 50.6, plus a 15 minus a 14.2 squared, divided by 14.2, 17 minus a 24.3 squared, divided by 24.3, plus a 17 minus a 14.9 squared, divided by a 14.9. And then you basically get the number. So now you have to look for the degrees of freedom. So we have 2 rows and we have 4 columns. Okay, so remember that. So our x squared value, your calculator gave us whatever the observed minus expected, and then you square that, divide by expected, and then sum all for all 8 is 4.466, about 4. Let me write it a little straighter. 4.466 approximately. And then your and then you have a degree of freedom, right? You have 4 column. You have 2 rows and 4 columns. So the expected value, the degrees of freedom is just the amount of rows minus 1 times the columns minus 1. So we have 2 for rows, 4 for columns. So 2 minus 1 is 1, 4 minus 1 is 3. So 1 times 3 is just 3. So your degrees of freedom is 3. And the alpha level is 0.05, right? Usually if they don't say it's 0.05. And then let's kind of draw a general picture of how this looks. So we have a skewed. So let's say you have something like right here with a 4.466 x squared value. You draw and then you color it in. So any area bigger than this. So now let's find the p-value. So I'm using an n-spire, so go in your calculator. So I'll only be using n-spire. I don't know how to work with 84. So basically you press menu, press go down to probability or statistics, and then go down to distribution, which is number 5. Then go down to x CDF, so number 8. The C one, not the P one. So x squared CDF. Lower bound, looking at our picture, is the lower is 4.466, right? And our upper bound is 9E999. So I usually write E999, which is just a really big positive number. So you could put 1,000, 2,000, 1 million, or etc. I don't care. But basically, it just has to be a really big number. So if you want to write 9E99, just put a 9, and then you're using n-power. Go to the left side of your calculator, and go down and you see a EE button, just press that once. That'll give you the E. And then it's just right above the pi symbol. So, and then you probably 999, like three times to get the 999. So that just stands for a really big number. And your degrees of freedom is 3. Okay. And press OK. And you get a p-value of 0.215 approximately, right? So your p-value is obviously 0.215 is obviously bigger than 0.05. So it's not really that unusual because 20% of will base 20%. We have a 20% chance of getting our sample that's not equal to our basically that distribution. Basically, that's what that means. So we just need to write that out as a conclusion. So our conclusion would be based on the p-value, the p-value of I think it was 0.215, I think, which is greater than the alpha level of 0.05, I fail to reject the null hypothesis, right? And we say the alternative hypothesis is true. So you have to write this in context. I'm just running out of space and I don't have room. So basically, you write based on the p-value of 0.215, which is greater than the alpha level of 0.05, so it's be greater than your alpha level. I fail. I fail to reject. You have to write that down. I failed to reject the null hypothesis. So it will be like I failed to reject the null hypothesis that gender and favorite chocolate color are independent of each other, and that basically states that you fail to reject that null hypothesis. So you say that that the sample that the gender and favorite chocolate color are independent. So you say the null hypothesis is true, and then sorry, I wrote this wrong. This one's false. So then you have to state that your alternative hypothesis is false. So your first sentence is about your null hypothesis, and your second sentence about your alternative hypothesis. This is always for the case for your conclusions for any test, the z-test, the z-test, the t-test, and the chi-squared. So you have to say, and then you say there lack evidence to suggest the alternative hypothesis that that gender and favorite chocolate color is independent is true. So there lack evidence to state that the alternative hypothesis is true. So you're saying that there isn't enough evidence to say that they are not independent of each other. You know. So they're not saying that there's no evidence. They're just saying there's not enough evidence to say that they're not independent, basically. So that's what we write for our conclusion. Okay. So if you want to do this all by like just your calculator, basically and you're using Inspire, what you do is that let's go back to our chart, right? So we're just gonna be focusing on this chart right here, right? We only care about the sample. We only need to plug in the sample. So it's the same idea with the chi-square test of homogeneity. You press menu, go down to matrix, number 7, then go to 1, which is create matrix, and then create 1, which is matrix. Number of rows, you have 2 because of boys and males and females, right? And then number of columns is 4 because you have red, blue, green, and yellow. And then press OK. So you just plug in the numbers. So you plug in 91, 26, 53, and 26. And then you plug in 55, 15, 17, and 17, right? And it will just give you, and then you press enter, and you basically just get the exact same matrix. So you have a matrix like this with like 4 numbers, right? And you just place each one individually. You don't have to write these numbers, basically. You only have to write these. So this one's right here. This one's this one right here. This one's this one. This 17 right here is right here. You know, just put it at the right place. Like the order does matter. You have to put it at that right place. So you have 8 numbers, and you have to put in those 8 in that right location. Now use the up button on your calculator and go back to your answer. So highlight it has a blue highlight over your basically your your matrix. Control C. It's hold down Control and then press C. So you could tell that it works because if you go back down using your down arrow, press Control V, you should it should basically paste your matrix. So it's your calculator is kind of like a computer. It would just use like Control C, so it does know how to like copy and paste stuff. So now go down and then go press Menu. Go down to Statistics, number 6. Go down to number 7, which is Stats Test. Then go down to number 8, which is X squared two-way test. And press that one. And then your observed matrix, just Control V. So that will post your. That's why we Control C the matrix, because now we just Control V and put the matrix in there and press OK. Right, and then we basically get our entire calculator. Our entire calculator will give us everything. So title X squared two-way test, which is basically a two-way test, will help us. As our previous video, we used this to get the chi-square test of homogeneity. Now we use it to get the chi-square test of independence. So this is just a chi-square test of independence. Our x squared is 4.429, which is really similar to what we got. It's just that our values for our expected table right here, right, are bounded by like to the 10th decimal place, so to 1 decimal place basically, and it's not as precise as possible. While like the calculator would do a bunch of decimal places, and this is why it's more precise. And then we have a p-value of 0.219, kind of rounded. And our p-value was like about 2.215, and that's because we were rounding from our x squared value of like 4.4 something, right? And that's because of our expected value chart, as I said before. So it's not that much of a difference. It's okay. Our degree of freedom is 3, which is true because we have 2 for our rows for males and females, and 4 for our colors for red, blue, orange, red, blue, green, and yellow. So that's 2 minus 1, which is 1, and 4 minus 1 is 3. So 1 minus 1 times that 3 is 3. Degree of freedom is 3. And if you don't want to do the expected matrix, basically, you see the expected matrix on the bottom. It tells go down using your down arrow. You press your var button, and then go down all the way to stat exp matrix, which just stands for statistics expected matrix. Press that one. Press enter, and then press enter again, and then you basically get your entire matrix. So you get a 9.53666 infinitely, right? That's why I said like they're expected for the calculator is more precise because they have all these decimals. And you have 26.78 and a bunch of sixes instead of 26.8, right, for male blue. And then you have 45.73 and repeating 3, 28.09, repeating 4.906, right? They're pretty much all similar. They're basically like the exact same numbers, except ours is rounded. So it doesn't matter if it's rounded. If you have like a general idea, like you're gonna fail to reject either way. Even if it's like 0.215 versus like 0.219, like they're both bigger than 0.05. Like that basically would just fail to reject, and your test will be fine. Well, okay. Well, that basically covers everything for the chi-square test of independence. Thanks for watching, and I'll see you at the next math record.